plus something. By the way, this is exact. But what I'm going to do with it is I'm going to throw that away. Because I don't know what C bar is. I didn't know what C1 was. I didn't know what C2 is. I certainly don't know what C bar is. And my approximation is going to say, throw this away. So when I think about this term, notice it has this delta t squared in front of it. So presumably if delta t is small, I could probably throw it away. What kind of error do I make? Well, delta t is 10 to the minus 2. I'm making an error of 10 to the minus 4. I divided by 2 delta t. Minus. Sure, if you want minus sign, we could do that. Satisfied? Okay. You want another thing in there? You want an A? No. Point is, I'm throwing it in the trash. And all I got to know is that there's a delta t squared multiplying it. That's the most important thing. So the delta t squared tells me the order of my error. And that's what we're going to throw away. So you get back this very intuitive result that you already knew. Slope is rise over run. Again, this goes right back to like first couple days of calculus lecture. But we're going to use that here because this is actually fundamentally what you're going to do. Remember, when you are solving an equation, the first thing you are ever going to do is say, if I have these functions f, you're going to do what's called discretization. You are only going to evaluate this function f at certain points. You pick where those points are. There's no longer this idea of continuity. Okay? You discretize. You pick points, and you fix them. And those are the points you're going to compute everything on. Okay? There's no longer evaluating the function here and here in between. Right? F is a continuous function. You can evaluate it an infinite number of places. And then as soon as you go to the computation, you say, no, if I break this up into 100 points, there's only 100 points I have values for. I could interpolate values to get in between. But that's it. This is the discretization process, which also allows you to do this stuff. Okay. So that's that. Now, in the notes, from there, I go on to say, hey, check it out. You can pretty much do the same kind of Taylor expansion idea to get other derivatives. So for instance, what did I do here? Remember, I did something super fancy, and I subtracted this from this. This from that. What happens if I would have added them like I tried to do at first? Well, if you add them, you get this added to this, these two add, these subtract, these add, and I actually want to keep the Taylor expansion for one more term because these would cancel and then you get a term up here. And by doing that, I could actually calculate a second derivative. Okay? And in fact, the second derivative, let me write it down here. If you add those, so subtracting gives me the first derivative. Adding gives me a second derivative, which looks like this. Really simple to show this. Point in front minus twice the current point. Point behind divided by delta t squared. And here's what I threw away, or what I'm going to throw away. There's your second derivative formula. What you use is your neighbors to calculate derivatives at your current point. Okay? So if you're evaluating the derivative at this point here, you use your two neighbors to draw your slope for yourself here. If you're calculating a second derivative, use neighbor over here, twice yourself. You get yourself your second derivative formula. Okay? So there's a table in the notes. I think they're called tables 16, 17, and 18, which gives you what are called center difference formulas. Center difference because what you're using is you're weighting the neighboring points equally. There's also called forward difference and backward difference. You do not have to use that neighbor over there. I could use the neighbors on this side. Maybe this neighbor over here is not nice. So I'll just talk to these neighbors. I can still calculate a formula that's delta t squared accurate. Okay? And it's also important to think about forward and backward differencing because what happens when I solve this boundary value problem? Actually, let me draw it over here. let's say this is A, this is B, and I have some solutions going to look like this. My job, first of all, is going to discretize it. So let's think about discretizing. Here's the points I'm going to solve it at. I'm just making this up. Let's say that's it. So for instance, that point over there, who are its neighbors? Do you guys want to sing it? Who are the, no, people in your, no, neighborhood. No, you guys don't know that? Seriously? Come on, that's Mr. Rogers, right? Tell me you guys know that song, right? You guys know that who are the people in your neighborhood? In your neighborhood. Okay, thank you. I'll provide you with a YouTube link after class so you can get yourself educated. All right. All right, so there you go. So over here, if you're trying to calculate a derivative there, you better use points over here because there is no neighbor over there. Okay, that's it. So you need forward and backward difference formulas, pick out your accuracy, and you can get yourself a scheme. Now, how does it apply to this problem originally that we wanted to solve? So let's go through this and actually use these ideas right there with that boundary value problem. Okay, so we're going to solve this now. And one thing you should understand very clearly about MATLAB. MATLAB has a purpose. And its purpose is to solve that. That's why it was invented. The guy who invented this, Cleve Moller, this is what he did, matrix computations. Everything's about AX equal to B. Okay? Almost everything we're going to do in this class ultimately is going to result down to an AX equal to B. Okay? So, and this will be an example of that. AX equal to B. That's what your whole mathematical existence will come down to, is that. And how to get AX equal to B quick. Okay? Because we're going to get big matrices here when we do computing. All right, so let's go back to this problem and start implementing what we just learned. So first of all, what I have here, second derivative. All right, big deal, second derivative. Let's write it down. Let's write that equation down now in this discretized form. That minus that plus this all over equals. There's a second derivative, my approximation, times P of t times dy dt. Oh, dy dt, that's pretty easy too. T plus delta t minus y of t minus delta t all over 2 delta t plus q of t y plus r of t. Anybody see any derivative in there anymore? What I replaced derivatives with was relationship between neighboring points. Okay? Because that's what finite difference tells me to do. It just says, look, slopes are just, you know, or derivatives are just slopes, and so that's just using neighboring points to calculate a slope. So I don't have any derivatives left anymore. So this is what we have. I'm going to multiply by both sides by delta t squared. Now, do you guys hate it when I do this, if I just start erasing? All right, so I'll write the whole thing out. All right, multiply by delta t squared. What do you get? Left side, the delta t squared cancels off one of those, right? So then I have delta t, p of t over 2, and then I have y of t plus delta t minus y of t minus delta t plus q of t. Actually, there's the delta t squared on this one. Q of t, y of t, plus delta t squared r of t. Okay, there we go. Now I'm going to start collecting terms that look alike. So I have y of t plus delta t here. I have another one over here. I have y of t's. I have y of t minus delta t's. So let's collect them all together. So how many y of t plus delta t terms do I have? I have one right here. I have this one here. And when I bring it to the other side, I change signs. I get minus delta t p of t over 2. Great. Plus, I have my y of t terms. How many of those do I have? Minus 2 of them here. And on this side, there's none here. There's none there. Here's some right there. I'm going to move it to the other side. So get minus delta t squared q of t. That's it. How many y of t minus delta t terms do I have? Well, I have one here. There's another one there with the minus sign, so when I bring it to the other side, it's plus. So plus delta t, p of t, 2. And then what's on the other side is still this delta t squared, r of t. There we go. Right. So I wrote this down, collected everything. And my claim is that this here is simply ax equal to b.